Good afternoon, kiddos, or good whatever time of day you happen to be watching this, but it's afternoon for me. The afternoon of November 4th, yeah. Day after our election. Still not sure who the president is, but you know what I do know? I know the Dodgers are World Series champions, and the Lakers are NBA World Champions, so we got 2 wins this year, regardless of what happens in our presidential election. And with that, I welcome you to another thrilling episode of Mr. Smith Talks About Calculus. And in today's episode, we will be tackling at least part of, not sure about all of, because it's a big section, and I am of course talking about 3.5 in Louis Lighthold's The Calculus 7, which deals with concavity, points of inflection, and second derivative test. Sounds like a mouthful because it is. So, without further ado, let's go ahead and get started. Share screen, advanced, content, camera, share. So, what you should be looking at is my notebook underneath my document camera. And you'll see that I've already updated and gone ahead and written out the title of today's section, which I just told you was concavity, points of inflection, and the second derivative test. So I'm going to do my best to kind of walk through this slowly. The main idea here, I do not think is that difficult. Okay, once we kind of approach it and think about it, what we're going to say here makes sense. But as calculus is wont to do, it tends to get obfuscated under a lot of jargon and theorems and definitions. Okay, so we're going to start out with this picture and just talk our way through everything that we're about to say in technical calculus speak, but just see if we can kind of intuit our way to what this whole lesson is about. And what this lesson is about is the second derivative of a function and what that can tell us about the function and its graph. Okay, so you might be thinking, oh, Mr. Smith's second derivative, I can barely get the first derivative. But that's not true. I think you understand the first derivative better than you think. And the way that I've been having us visualize the first derivative and how its behavior relates to the function in question is by like the surfboard, okay, which I've been using my green tongue depressor. That the first few sections of this chapter, we've been using the derivative and the fact that it gives us the slope to this tangent surfboard to zero in, pun intended, on locations where we might have maximum or minimum values. And the way that we do that is by realizing that if this surfboard in its journey along this function wave gets horizontal, that could be a location where we have an extremum, like we see here. Okay, so kind of tracking this surfboard, it goes and gets horizontal. We check that with the first derivative test and see, oh yeah, we've gone from a positive first derivative, a positive slope to our tangent, zeroed out, and then on the right side of that point, we are now a negative slope, and thus a negative tangent. And so B, labeled here, is indeed a maximum, which we can verify through the first derivative test. And then we keep going, and we're negative, and we're negative, and we're negative, and then we start approaching this other horizontal point. We check it with the first derivative test and see, oh, yeah, we've gone from a negative slope to a positive slope. There's another extremum, in this case, a minimum. And we go along our way. And of course, not shown in this picture is that we could also have situations where there is no first derivative because of the existence of a cusp or a corner where we still have a max or a min. So those are kind of like the key points we're searching for with the first derivative and what they can tell us about the function itself, the behavior of some curve. We can glean a lot about it if we know what the derivative is. So we're going to start that journey over with our surfboard, but now have in our brains, what is the second derivative doing as we take this wave, as we surf along this wave? And before we start that journey again, let's think about what a derivative is. Okay, the derivative tells us how is something changing right now. Okay, so the first derivative tells us, oh, okay, this function is increasing. Then it stops increasing, and now it's decreasing. Okay, it tells us that instantaneous rate of change. So the second derivative, by that very same logic, needs to tell us the instantaneous right now change of the derivative of this green surfboard. So that is the mental picture we are taking into this as we go, okay? Because it does take a bit of a mind shift, a mental shift to kind of wrap your head around, okay, what is the second derivative telling us about the first derivative? And then, as we'll see today, what is the second derivative telling us about the function itself? So let's just start from A, and we've got a first derivative that goes like that, okay? Now, if there was some intermediate point in between A and B, and we looked at the derivative at that intermediate point, maybe right there. Watch that again. We've gone from tangent there at A, tangent there at B. How would we say that the slope of that line has changed between those two locations? It got less steep. Sure, great Algebra 1 answer, we can run with that. This point has a steeper tangent line than this point. They are both clearly positive tangents, or slopes rather, but this is steeper and this is less steep. Okay, let's try to translate that into maybe some calculus level intuition. If we've gone from a steeper tangent line to a less steeper tangent line, what has happened to the slope of that line? Pause now for commercial break and ponder. Well, if we've gone from a steeper to a less steep, the slope has decreased. Okay, maybe this is a slope of 7, maybe this is a slope of 5. 5 is less than 7. The rate that we are changing, or the way that we are changing, is decreasing. So we would expect that from here to here, our second derivative is negative, okay? The way that our first derivative is changing as we move from A towards B is that it is getting smaller. It is decreasing. We're going from positive numbers to smaller positive numbers, okay? And let's watch, if we were to kind of characterize this movement, this surfboard is moving clockwise. The rotation that we see with this lessening tangent line, with this second derivative that's negative, is counterclockwise, okay? And then we get to B, and our first derivative is 0. So now let's do that same exercise again. Let's say we go from B, this tangent line, to something to the right, like there. Okay. This is now a negative tangent. We've gone from 0 to negative. So how is that first derivative changing? It's still decreasing, because a negative slope is less than 0 slope. And so we still see this this clockwise rotation of our surfboard. Still negative, still decreasing, still getting more negative. So now steepness is not a very good measure, because this steepness actually means we're still decreasing, because we're getting more negative. then hopefully you can see somewhere in here, we are still going counterclockwise, 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 oh, and then it pauses. And then somewhere in here, we start rotating the other way. We're still negative, but now we're going from steep to less steep, which in the context of this negative slope means that we're getting less negative. We are increasing. Whoa. I'll do that again. So we've gone from there. We're going counterclockwise, clockwise, 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 counterclockwise, counterclockwise, counterclockwise. Something important is happening there. When we make this shift from a clockwise rotation to a counterclockwise rotation, in terms of the second derivative, we've changed direction. We've gone from our first derivative decreasing, decreasing, decreasing to, oh, now we're increasing, 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 decreasing. So the second derivative is telling us something about the change of our first derivative. Okay. So we'll call this C x3 y3. And the important thing that's happening here, that's in our title, is that somewhere in here at that point where we were still going clockwise, we were still decreasing, at that change point where we went from a negative second derivative to a positive second derivative, that's an important location. And in fact, we call that a point of inflection. Point of inflection, where that change in the sign of our second derivative happens. So we're freewheeling here. I'm going a little off script, but I think doing this kind of like talk through, feel this out before we get into the scary terms, I think that'll be helpful. So that point D is a point of inflection. Furthermore, that whole clockwise, counterclockwise game we were just playing tells us something about the behavior of F. You'll notice, like, just like looking at this graph, some of it's kind of like cupping down and some of it's cupping up. Cupping is maybe not the most mathematically sound way to say it. In fact, the way that we say it is concave. Okay. That as we had this counterclockwise, sorry, I keep saying counterclockwise, I mean clockwise. When we have this clockwise rotation of our tangent and thus a negative second derivative, our graph is like pointing down, it's concave down. At those locations where our first derivative is rotating counterclockwise, thus increasing, thus indicating a positive second derivative, we seem to be kind of cupping up, concave up. And in fact, that is the power of, or one of the powers of the second derivative. That where we have a negative second derivative, where our first derivative is decreasing, our graph is going to be concave down. When we have an increasing first derivative, visually represented by a counterclockwise rotation to our tangent line, our graph is going to be concave up, which correlates to a positive second derivative. And at this point here is the changeover. The point of inflection is where we go from a downward facing, a concave down section of our graph, clockwise, and then we kind of stall out, and then we inflect up, and we're concave up. Okay, so that's what we're doing this. Oh, and then one last thing. What the actual second derivative test is with that notion of, okay, positive second derivative means we're concave up, negative second derivative means we're concave down. We now have a cheat code for our critical points finding maxes and mins. instead of using the first derivative test and looking left and right, with the second derivative, and we'll come back to this obviously, the second derivative allows us just to say, hey, there's a critical point. What is the value of the second derivative there? If it's negative, meaning concave down, that's a maximum. If it's a positive second derivative, meaning concave up, then that's a minimum. And that will simplify, or can simplify, our max and min search. Just, oh, take the second derivative. What does it say at that point? Whew. Okay, so that was kind of me just talking through what we're about to do. Hopefully that registered with some of you. If not, I apologize for wasting your time, but you know, you're kind of a captive audience, so deal with it. So all that said, we're going to jump in and just pound you over the head with some definitions. But a lot of the stuff I have mentioned right here. Okay. So starting with concave up and down, which you sort of just touched upon, but this is 3.5.1. Definition of concave upward. And they're going to give like a very heavy-handed explanation of this. And we're going to write it down because we're good little calculus students. But I'm definitely going to translate this a little bit because that's what I do. If something smells kind of fishy and kind of overly highfalutin, as it were, for example, your math teacher just casually using the word highfalutin, that's a little highfalutin itself, we're going to sniff that out and just say, hey, if it's too fancy, let's make it simpler. So here's the highfalutin. I don't even know if I'm saying that word right, but that's why I teach math. So the graph of the function f is said to be concave upward. Said by who? I don't know. Me, I guess. Concave upward at the point C, comma, f of C, if the derivative of f at C exists, and if there is an interval which we'll call uppercase I, a little bit. Okay, so sure. Whew. Containing C, such that for all values of x that are not C, x not equal to C, in I, the point x comma f of x is above the tangent line to the graph at C, comma, f of C. What? Let's go back to the surfboard. Something I didn't point out specifically earlier. If we are concave up, so just anywhere kind of in this section here, let's consider what is happening with our tangent line relative to the graph of f. Well, what's happening is if you chose some point at random in there, and you drew this tangent line, and then you looked at a bunch of points kind of close to C from the definition, or that point we just drew, all the points on that graph close to that point lie above that green surfboard, okay? The tangent line is below the graph, okay? Concave up sections of our graph have this characteristic that if you draw a tangent line at a given point, the stuff around it is above it. And as we'll see in a second, it's the exact opposite for concave down. That when you do a concave down section of a graph, when you draw that tangent, the tangent is going to rest above all these points, okay? So that's all that this fancy definition means. You draw the tangent, if the points around it are above the line, it's concave up. If the points around that tangent are below, it's concave down. Okay? So that's what we're going to say for our definition for dummies. Not that any of us are dummies. I don't know, maybe some of us. Definition for dummies. Concave up means graph is above tangent line or you can alternatively think of that the tangent line is below the graph. Whatever floats your boat. I think being familiar with both is important. The tangent is below graph, and then rotationally, our surfboard, when we're concave up, when our second derivative is positive, when our rate of change of our first derivative is increasing, rather positive, I think is a better way to say that, means that we are rotating counterclockwise. Cool, 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 cool. And then we have a similar kind of stuffy example or definition of concave down, which, to be honest, let's just skip that. We'll go straight to the definition for dummies. So 3.5.2 definition of concave downward for dummies. We're going to skip the math speak one. And it's just the reverse of this. That if we're concave down, it means that your points are below the tangent, or conversely, that your tangent line is above the curve. Okay, cool. And then we will also figure out what does that mean for the rotational aspect to our first derivative. Concave down means graph is below tangent or tangent is above graph. Rotationally, concave down means that our first derivative is getting smaller, which means that its rate of change is negative. Second derivative is negative. So rotation is clockwise. Cool. Cool, cool, cool. And then what we actually care about and what we will actually use, well, we care about this, but the analytical thing that we will do with this information about concavity is use the second derivative. And so we have a theorem, 3.5.3, that turns this into an analytical tool for us. Okay, well, how do we figure out where these concave up and concave down sections are or points are? Well, we analyze the nature of the second derivative at a particular point or on a particular interval. And so the theorem has no name, it's just theorem. Maybe let's say how to determine concavity. It sounds like you just think cavities, you know? Something you don't want to hear at the dentist. Well, you've got a concavity on your 7th molar. We have 7 molars? I don't know. Miss Rice would probably know. She comes from a family of dentists. And the theorem says this: if we let f be a function that is differentiable, that's a funny word, on some open interval containing C, then two things are true. Two conditionals. If f double prime, the second derivative of C, is positive, is greater than 0, the graph is concave up. And let's be specific. The graph of f is concave up at that point, C, f of C. And segundo, if f double prime of C is negative, less than 0, the graph of f is concave down at C, comma, f of C. Pretty cool. The second derivative gives us the means to determine the concavity of a function at a given point or on an interval, which is just fabulous. Okay. Maybe it's not fabulous to you, but it's pretty fabulous to me. So then that tackles like a big part of what we just talked about, concavity, using the second derivative to determine that. But then how do we figure out the changeover from clockwise rotation of our surfboard, concave down, concave down, concave down, concave down, concave up, counterclockwise rotation? How do we do that? Well, one thing we should notice is as we approach that point, our second derivative is negative, 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 and then it's positive, positive, positive. It goes from a decreasing first derivative to an increasing first derivative. The second derivative, in other words, has changed sign. So now we see where we're headed. Kind of like the first derivative test, that if we notice this change in the sign of our second derivative, well then, that means we have a point of inflection. Yeah, duh. You knew that. Well, maybe you didn't, but now you do. So, which is basically exactly what we're about to write down. That intuition, the change from a negative second derivative to a first second derivative, indicates the existence of a point of inflection. Okay, and again, it's going to be sort of like a stuffy definition, but we'll translate it into basically what I just said. That's basically the definition. You change signs of your second derivative, you've got a point of inflection because you change from concave down to concave up, or vice versa. I don't think that's how you say that. Vice versa. Don't judge me. Whew. Lukewarm coffee at 156. 156. 56. Sweet. We're cruising. Maybe we'll get through all this. I don't know. There's a lot here. We're going to keep going until I have to leave. So I'm in it for the long haul, guys. I could be at home watching Around the Horn. Pardon the interruption. It's a good back-to-back on ESPN, but no, I'm here. Laying it all out there for you guys. Mr. Smith talks about calculus. Let's go. 3.5.4. 3.5.4. Definition of a point of inflection. You already know this. No big deal. Definition of a point of inflection. It's that changeover point we were talking about. Going from concave up to concave down to concave up. And it's when our second derivative changes signs. So let's formalize that. And the formalization says the point C, comma, f of C is a punto de inflexión, point of inflection. C, I don't know how to say graph, la pictura de la función f tiene una línea de tangente y C, I don't know, that's about as much Spanish as I got, sorry about that. Point of inflection of the graph of the function f if the graph has a tangent line there So that is an interesting turn of phrase. If the graph has a tangent line there is a distinctly different thing than saying if f is differentiable there. Because a graph can have a tangent line without having a derivative. What, Mr. Smith, you're talking crazy. No, I'm not. Oh, you dirty dog. The vertical tangent line. There's a tangent line there, but it's not differentiable. Okay. So that's, just keep that in mind. Might come back. So it has a tangent line. It could be a vertical tangent line, but it has a tangent line. And if there exists what do there need to exist? An open interval containing C such that what? If X is in Y, sorry, X is in I guess I is going to be our interval, sure. Snuck that in there. Then either two things are true. One of two. That is not how you spell then. Then either f double prime of X, sorry, f double prime Yeah, this is right. F double prime of x is less than 0 if x is less than c, and f double prime of x is greater than 0 if x is greater than c. There's that changeover. We've gone from negative second derivative to the left of c. As soon as we get bigger than c, we've gone to a positive. We've gone from concave down to concave up. The second way this can happen is in reverse, that f double prime of x is greater than 0 to the left of c, and the second derivative is less than 0 to the right of c. So in this case, we've gone from concave up to concave down. Sorry, I didn't think about that. And that happens sometimes. You're like, this is kind of new, and you're trying to think, which way? That's okay. Take a deep breath and just think about it. If our second derivative is positive, that means our function line is increasing. Slope is increasing. We are concave up, and then we switch to concave. We switch to second derivative negative, means that suddenly our rate of change of our derivative is decreasing, is negative, and now we're concave down. Okay. So that definition for dummies, because that was kind of a lot, but it's kind of easy. Like it's not that stuffy. It just says there's c, comma f of c. If at that point you have a change from a negative to a positive second derivative, or vice versa, that's a point of inflection. Cool. And that's what our definition for dummies is going to say. Definition for dummies says, if the second derivative changes signs, and the tangent line exists, which again means that if it's like a cusp situation, even if it's changing concavity, it's not a point of inflection. It needs to be a smooth changeover where you actually have a tangent. And the tangent line exists, we call it a point of flexion. Point of flexion, point of inflection. Or if we're going to keep thinking about the surfboard, it's that moment where we go from clockwise to counterclockwise rotation, or vice versa. Or going from clockwise to counterclockwise rotation, or vice versa. Cool. And then we're almost ready for our first example. Almost. Do we need to do this theorem? Yeah, we do. Okay, so this theorem is kind of a tricky one. It seems like it says something, but it doesn't. So I'm going to warn you ahead of time, this can be kind of tricky. That there's not like a hard and fast way to find these points of inflection. Well, that's not true. There is, but we have to exercise caution. That we're going to be hunting for points where our second derivative is either going to be 0 or non-existent. Okay, because those are going to, and so that's kind of similar to the first derivative game we play. And what this theorem says is that if it is differentiable to the second derivative, the point of inflection is going to correspond to a point where the second derivative is 0. It's not saying that everywhere you have a second derivative, that 0, you have a point of inflection. We will see examples of why that would not be the case. But what it is saying is that if you have a point of inflection and if you have a second derivative that exists, that second derivative is 0. So it kind of goes back to that sufficient and necessary thing, that a second derivative being 0 is not sufficient to say that a point of inflection exists there. But if there is a point of inflection and you know that the derivative exists, the second derivative exists, that is sufficient to say that the second derivative is equal to 0, which, as I'm saying that, I can see you guys kind of rolling your eyes like, wow, that's confusing. We'll kind of deal with it case by case, but we do need to write this theorem down, which is 3.5.5. And what it says is, suppose the function f is differentiable on some open interval containing C and the point C, f of C, is a point of inflection of the graph of f. Then, if the second derivative exists at C, then that second derivative is equal to 0. So a lot of conditions there, a lot of conditions. If you got a point of inflection there, and if it's differentiable, and if the second derivative exists, then the second derivative is 0. But there's a lot of hurdles to clear there. Okay, so it's not saying the reverse, and it's very tempting to want it to say the reverse. It's not, or I guess the converse. It's not saying that if you have a second derivative equal to 0, then that's an ironclad promise for a point of inflection, because it's not. So I just want to be as upfront with that as possible. This only works that way, not that way. Okay, so all of that said, I think we are finalmente ready for an example. Whew. Maybe, possibly. Which one are we going to do? We're going to skip straight ahead to example 1. Skip all the illustrations. Nobody cares about illustrations. Maybe we do, maybe we don't. Okay, example 1. Example numero 1. They give us a function and say, find the point of inflection of the graph of f and determine where the graph is concave upward and concave downward. Support the answer by plotting in the same window the graph of f and the inflectional tangent. Oh, that's fancy. Can we do that? Sure, maybe. What's our function? Our function is f, because it's always f. Not always f, it's mostly f. F of x is equal to x cubed minus 6x squared plus 9x plus 1. Okay, so I'm going to cheat here. I'm not cheat, I'm just going to go out of order. Let's see what this thing looks like. So that's going to kind of inform what the heck is going on here. So in our graphing utility, we are going to say, what is this? X cubed plus, nope, minus 6x squared plus 9x plus 1. All right, kind of cool. Let's maybe zoom in a little bit. Definitely don't need that much x. Like -5, 5. Here's like Positive 10? I don't know. Let's see. All right, pretty cool. Pretty cool. So if we're going to do our surfboard game, what we're looking for and what we're going to try to analyze here is when is this thing concave down and when is it concave up and when does that shift happen? Okay. So let's go for a ride. We're surfing this wave. It's definitely a positive first derivative because that is a positive slope to our tangent. And as expected, that means our function is increasing. But the way that our surfboard is changing is that it is getting less positive. It is decreasing. Thus, our second derivative on this part of our graph is negative. And as we see, the result or the consequence or the correlation is that our graph is concave negative. Concave negative, concave down. We see that there's probably a maximum here. So we're probably going to do a first derivative test here just to verify that. But we're still rotating clockwise, so we're still concave down because we still have a negative second derivative until somewhere in here we're going to hit this point where we start rotating the other way, where we start increasing that slope of our derivative. And then just for all time, we're concave up because we're just getting steeper and steeper and steeper. So our goal is to find where is this crossover point. And the second derivative is going to lead the way. Okay, but we'll see that we're going to kind of just build on the stuff we've done and also do pit stops to figure out, okay, where is this max and where is this min? And using the first derivative to do that. So we're going to end up with some like kind of beefy charts where we're going to track the behavior of the function, the derivative, and the second derivative all in one compact location. Okay, so let's first of all differentiate this twice. So our first derivative, f prime of x, is equal to 3x squared minus 12x plus 9. And then our second derivative is equal to 6x minus 12. Both these derivatives exist everywhere because they're polynomials. So we're only interested in when these are equal to 0. So f prime of x is equal to 0. When that guy is equal to 0, which we're going to make it look like that guy. Beautiful. And so our critical points for our first derivative are x equals 3 and x equals 1. So that'll definitely be part of our chart. And then again, our second derivative exists everywhere, but f double prime is equal to 0 when 6x minus 12 is equal to 0 or when x equals 2. So these 3 points are going to form kind of the fence posts, if you will, for our chart. So we're going to build this out much like we did in previous sections. We'll have an interval kind of dictated by these points. Where appropriate, we will evaluate the function. Hello there.
Hey, how's it going?
Good. Let me
Got
just.
a big class here today.
This is
Dr. Merwin.
How you doing, Dr. Merwin?
All right.
One sec.
Sorry to interrupt.
No, I'm just. Oh.
This is probably your.
Alrighty then. Sorry for that brief pause. A couple of my bosses walked in, so you know you always got to make time for your bosses. Dr. Baker, our principal here, was doing the rounds with one of our assistant superintendents from the district, who's like an even bigger boss. So we talked shop for a little bit, and that's why I had to pause. So hopefully that was not too big of a break. So let's keep going with example 1, because we had just, I guess I should show you my doc cam now. So we had just figured out some of the critical numbers for our function, that our first derivative zeroed out at 3 and 1, and then our second derivative had a 0 at 2. And so we're going to kind of figure out, what is that going to tell us about our function? Combining what we've already kind of worked through with our first derivative, and now this new knowledge with our second derivative in terms of concavity and points of inflection. So we're going to have a column for f of x and actually find some function values where appropriate, because eventually it'd be nice to kind of build out a graph if we wanted to. And we'll have an f prime for our first derivative and an f double prime for our second derivative, and then we'll make a conclusion about what does all this mean together. The intervals we're going to look at are going to be centered around these 3 points. So we're going to care about when x is less than 1. I realize we haven't really been using interval notation a lot on these charts, which no reason we can't. We're calculus students. So from negative infinity to 1, when x is equal to 1, between 1 and 2, when x is equal to 2, between 2 and 3, and when x is equal to 3, and finally from 3 to positive infinity. So we're just going to go interval by interval and see what's going on. Some of these we will leave blank. We're not going to come up with a function value for an interval, but we could come up with, for f prime, if x is less than 1, and I guess we should have maybe listed what this was, but we can look back up here. So for less than 1, this will be negative, this will be negative, so that'll be a positive first derivative. For our second derivative, if x is less than 1, this is going to be negative. And so the conclusion we can make here is that with our positive first derivative, f is increasing, but with our negative second derivative, f is concave down. Cool. Cool. Okay, well then at 1, that's our first 0 of our first derivative. And if we wanted, we could have a function value 2. Plugging in a 1 here, we get negative 5, positive 4, we get 5. Our second derivative at 0 is still negative, so we're still concave down. And then we're gonna get a big hint for the finale of this section right now. That, okay, we've got this 0 here for our first derivative, which means we could have an extrema, but we need to look at the right side to figure out, okay, what happens to our derivative after this? Do we change sign? Because that's the first derivative test. Do we go from an increasing function to a decreasing function? So looking to the right here, if x is like 1.5, this will be positive, this will be negative, our first derivative will be negative. And so by the first derivative test, this change in sign of our first derivative indicates that we have a maximum here. And this right here, which we haven't even talked about yet, but this is the second derivative test. If you have a concave down point at a function or at a first derivative that is 0, you've got a maximum, which just makes sense. If it's concave down, it's a maximum. If it's concave up at that point, it's a minimum. Okay. The second derivative is still negative here, so we're still decreasing. And we're still concave down. So we're decreasing. F is decreasing, and we're concave down. And then at 2, we want to do that. 8 minus 24 is like negative 16, plus 18 is like negative 6, plus 1 is like negative 5. Did I do that wrong? Probably. Yeah, my notes say I did that wrong. 2 cubed is 8, minus 24 is like negative 16. Oh, negative 16. Plus 18 is positive 3, plus 1 is 4. Maybe. I don't know. I'm doing this quick. Don't judge me. F prime at 2 is negative. Still decreasing. But we get a 0 here. 0 here. Okay, so we can't really say anything yet about point of inflection until we see what happens on the other side. But we can say F is decreasing still. Now, to the right here, this is the definition of the point of inflection. If we have like 2.5 as our input, 2.5 on our second derivative, ho, 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 that's positive. Here we're still negative, so we're still decreasing. But now we are concave up. Oh, so this is kind of the second derivative version of going from increasing to decreasing. Going from concave down to concave up indicates point of inflection, or poi. We got a poi. We found it. Okay, and then working through the rest of this, at 3, we know our first derivative is 0. After 3, it's going to be positive, which means we have a relative max. We're going to be positive the rest of the way here for the second derivative. So F is concave up, which again, if we've got a maximum or a minimum with a concave up point, it's got to be a minimum. And then for the rest of the graph, we are increasing and concave up. Whew, that was a doozy of a first example. What time do we got? What time do we got? That little visit from the game squad kind of sent me back. 2:30. Oh, we've been talking a long time. Whew. We're gonna do one more example, and then I think I'm probably gonna have to cut this into 2, maybe, possibly. So much going on, you know? I might do 2 more examples. What did I do last year? Let's consult. Let's consult. Did I skip example 2 last year? Oh, the humanity. Example 2 looks kind of fun, bro. Yeah, we're doing example 2 for show. Example 2. Okay. Now our function is x to the 1/3, the cube root function. And we're going to see, well, first let's cheat. Why not? Let's just see what this looks like. See where we're headed. Or no, maybe let's not cheat. Let's see if we can figure it out and then see if it confirms what we're looking at. So f prime is going to be 1/3 x to the negative 2/3. And f double prime is going to be like a negative 2/9 x to to the negative 5/3. Ew, woof. So that's like 1/3 times the cube root of x squared. And this is like negative 2/9 times how do we want to do this? X times, yeah, cube root of x squared. Does that work? Hopefully. Yeah, why not? Okay. And we are looking for, when is this thing equal to 0? Never. When is this thing equal to 0? Never. That was fun. Well, when does it not exist? Oh, when x is equal to 0 for both of them. So that actually is kind of nice. So f double prime of x and f prime of x and f double prime of x does not equal 0 for any x, but both f prime of x and f double prime of x dne for x equals 0. Okay, so what this example is going to show us is that we can have a point of inflection even if we have a non-existent second derivative. Okay, so it's not, oh, you have to have double prime equal to 0. So we'll build out our chart, which will be a smaller one since there's only one critical point. Interval f prime, f double prime, and conclusion. And the intervals we care about are negative infinity to 0, x equals 0, and 0 to positive infinity. Wham bam thinking now. Okay. So when we are left of 0, our first derivative, well, we're squaring the input, so it's always going to make it positive, even if it's negative. That's going to be a positive first derivative. For our second derivative, you put a negative number in there, it becomes positive. This guy is going to be negative, which means this guy combined is going to be positive. Can I check out? Sure. Which means we are f increasing and concave up. Cool. At 0, we know that both these things dne, which could mean a couple things. It could mean we've got a relative extremum. It could mean we've also got a point of inflection, or it could mean we've got neither of those things. It's all going to hinge on what happens after this for both the first and second derivative. So when we have a positive x, well, we get the same result with our first derivative. A positive x plugged in here gives us a positive first derivative, meaning there is no extremum here. The first derivative test tells us, because there has not been a change in the sign of our first derivative, this critical point does not indicate a change, does not indicate a relative extremum. Okay? So it could be just a really flat point, or just like, or more likely it's going to be a, is kind of my guess. It's going to be like a vertical tangent, but we'll see in a sec. So then the second derivative, plugging in a positive here. This is positive, and now a negative divided by this positive denominator gives us a negative second derivative. That's the magic number. This is a change in the sign of our second derivative. We've got a point of inflection. So what we can say is f is increasing still. Now we are concave down. So analyzing this, f increasing to f increasing, that means no extremum. However, the change from concave up to concave down, from a positive second derivative to a negative second derivative, tells us there is a point of inflection. Woohoo! Let's see what that means for our graph. Y equals x raised to the 1/3. So window standard. No, zoom 6. No, let's get closer than that. That's not that fun. Window. Let's do like -3, +3, -3, +3. Oh, that's gonna be better. That's gonna be better. Oh, still not that cool. Let's go even smaller. -1, +1, -1, +1. Oh, there we go. It's that vertical situation, that vertical tangent. So clearly, we've got this increasing, and then we've got a tangent line, but we do not have either a first or second derivative. Okay. But because we do have that change in rotation from counterclockwise, stalls out, clockwise, we've gone from concave up to concave down. There is a point of inflection at 0, 0. Even though there's not a maximum or a minimum, because clearly there's no maximum. It just kind of increases, it stalls out at that vertical tangent, and then it keeps increasing. Pretty cool. Uno mas, they're screaming, no, no, no. Too bad. Yeah, doing one more. Uno mas. Por favor. Example 3. Now we're going to look at f of x equal to 1 minus 2x cubed. Really? Yeah. Okay, so let's jump straight into f prime, which chain rule tells us should be 3 times 1 minus dos equis squared. Derivative of this inner guy is like a -2. So our derivative is -6 times 1 minus 2x squared, which means that f double prime, again, going to have some chain rule going on. We'll get a -12 out front. We'll get 1 minus 2x, and then the derivative is -2, which means we get 24 minus 48x. Cool. Okay. What are we looking for? Non-existence and zeros. These are both polynomials. They're going to exist everywhere. They're going to be 0 when this guy is 0. So it's like when x equals 1/2. And oh, happy day, that corresponds with f double prime too. When 24 minus 48x is equal to 0, which also happens to be when x equals 1/2. That's kind of nice, just one thing to test. We'll build out our chart, interval f of x, first derivative, segundo derivative, and conclusion. And we're going to look to the left of 1/2, at 1/2, and to the right of 1/2. And make some conclusions. So first derivative, when we are less than 1/2, this quantity will be, let's think about this, positive, yeah? Yeah, positive. That makes sense. And this quantity will be, again, positive. Yeah, that makes sense? Lord, I hope so. Oh. Does that make sense? Like 0. Yeah, it's positive. Cool. So on that interval, f is increasing. Oh no, I'm a dingleberry. I'm a dingleberry. I'm a dingleberry. I'm a dingleberry. This is going to be... Smith, why are you making this so hard? This is like... This quantity is always going to be positive, no matter what we plug in here, because we're squaring it, and then it's negative. It's negative, you dingle. This is where I need a live audience to yell at me when I'm making dumb mistakes. I think this one's still positive. Yeah? Okay, cool. So f is decreasing and concave up. Now, we're going to have at 1/2, f is like 0, f prime is like 0, f double prime is like 0. So this means there could be a maximum or a minimum. I guess it would have to be a minimum since we're decreasing. There could be a point of inflection because we're got a 0, but maybe not. We have to see what happens when the other shoe falls. So when the other shoe falls and we have positive or greater than 1/2, our second derivative is still negative. Sorry, our first derivative is still negative. Doesn't matter what we plug in here, it gets positive, and then we multiply by a negative. So that's kind of lame, but it is what it is. And there's the bell. Talk to the bell. Bell to bell in an empty classroom. Woof. Then our second derivative, when this is greater than 1/2, I don't know, plug in a 1 here, that becomes negative. And so f is still decreasing, but now it's concave down, and we have seen that change. So no extremum, because we were decreasing, we're still decreasing, but we do have a point. We've gone from concave up to concave down. The sign of our second derivative has changed. So what does that look like? That looks like (1 minus 2x raised to the third Okay, let's change that window. Like, oh, that's cool. So it flattens out, which gives us that 0 derivative, but then it just keeps going negative. But there is a point of inflection because we're riding this wave going counterclockwise, 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 concave up, 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 and then we pause, and then we change direction. Clockwise, concave down, concave down, concave down, concave down, concave down. Wow. The power of mathematics to delight, to inspire, to encourage. Who could ask for more? Certainly not I. In fact, I offer no more today because that has already been a bit of a marathon session through 3.4, and we're 3.5, and we still ain't done. So we're going to look forward to a second installment of Mr. Smith Talks About Calculus 3.5. It should be a little bit shorter, hopefully a lot shorter. Otherwise, I'm going to cry. All righty. Good seeing you guys, or good you seeing me. I didn't see you. And I will hopefully physically see you quite soon. All right. Ready to go. Ready, go. Ready, bye. See ya.